Few things some few were suggesting to post the slides, and I think some of you probably have access to the last time the class was taught. The slides was up there, but I just put a link here, and also a Mathematica file that's being used. And just be warned that I'm may not be the best code that you see, but it works, and it is in the format that I'll update it too. If there are a few other things I add, I'll just upload it as well. So I have uploaded a set of notes on superconductivity and Cooper pairs and some amount of theory that we will need later on, not right away, but want you to kind of read through. Essentially, it starts with a more historical sort of discussion of how it was discovered, and three of the people who actually developed the microscopic theory of superconductivity, not necessarily, they developed the microscopic theory, and we'll look at that aspect of the theory as well a little bit in this course. So now. I wanted to just say that I'm somewhat in the interest of time. I'm stopping the discussion on scattering related transport. There's obviously a lot more one could do and discuss about it. But since I have given you an assignment, so your prelim take-home question, I'm trusting that you will pick that up by yourself. And whatever we have done in three-dimensional transport, if you go to lower dimensions like 2D electron gases or 1D nanotube, all that changes is the nature of the wave function, and you know how to handle it. You can use the effective mass wave functions. Instead of a three-dimensional effective mass wave function, you can have a 2D, plane wave, and in the third direction it's quantized. It's confined or a bound state. So you can rewrite the wave function, and then all of the physics essentially doesn't change after that, how you deal with transport. The matrix element and the density of states, the matrix elements and the density of states now are those of 2 dimensions rather than 3D, or 1D, so. Yeah. Okay, so 2D electron gases have certain transport. I'm just spending a couple of minutes summarizing that before I move to the next topic. And on the slides you will see a few ways it's handled. Some common tricks people use. You can assume a 2D electron gas to be a delta function in the z direction and spread out in the xy. That's a good approximation for graphene or 2D materials like that. But if you have a finite length of a quantum well, the wave function spreads a little, right? And so you can use a sine or a cosine sort of function. If you have a triangular quantum well instead of a flat quantum well like that, this is a form that is typically used. So instead of a sinusoid, you can use like a z e to the power minus z sort of function where it dies here and then it kind of or of course the exact solutions may be more airy function-like and all that sort of thing. Right? So there are some functions that are much more popular than others because you can infinitely differentiate, integrate it, and all that. Whereas and it's mathematically easy to handle, and that's what's used to calculate some of this transport. And of course, the biggest use of a 2D system is the fact that you can put the dopants or the impurities which you need to create the electrons far away from the path of the electrons itself. So the electrons are moving in a 2D plane here, but the dopants that might have created this electron gas are sitting out here, far away. And so when you actually look at the matrix elements, they get damped exponentially with the distance they are, because the Coulomb potential is obviously 1 over r. Right? But if you look at the matrix element, it takes it down as e to the power minus q times the distance. And if you just work that out, you'll see that the matrix element, the scattering potential in the q space or the momentum space, once you go there, it decreases exponentially with the distance you are. So beyond a certain distance, you make your sample or transport here completely, even though there are Coulombic impurities sitting here. That's not the limiting mechanism anymore. You can take it out of the picture now. And that's what has enabled over the years, sorry, where was that picture now? Oh, I don't even have that now. That has enabled over the past few years mobilities that exceed few millions and that sort of thing. I think I don't seem to have it here, but because of this, you can improve the mobility to a few millions, and that's what opened up things like fractional quantum Hall effect and gave birth to topological insulators and all that sort of thing. It came from very high mobility 2D electron gases, which were fabricated, grown, and designed to have extremely high mobilities by understanding all the details of the scattering mechanisms and then engineering it accordingly. So. Just give me a second. I thought I had it in the slides, but I don't seem to. Well, I guess I don't. So, so. Okay, so we'll and I've. So I'm starting a new topic now, but before I go there, if there are any questions on this last topic, I want to kind of just spend a couple of minutes maybe discussing, or any questions or things you want to, if you have questions of whether this will be covered or not later, we can also talk about that. So, none? Yeah. Okay, good. So let's then start this topic on superconductivity. And this is obviously a very exciting and interesting discovery. I think the most kind of very interesting situation is superconductors were discovered and way before any sort of understanding of semiconductors was in place. So they are in that sense much older than semiconductors. And it was discovered in 1911 by a group of Kamerlingh Onnes and others at Leiden in Netherlands. And it was not discovered because they were trying to discover superconductivity. It was a big accident because what they were, there was a big race at that time to reach colder and colder temperatures. So essentially and the goal was to liquefy air, liquid nitrogen or oxygen, to liquefy gases. And the way to do that was to go to lower and lower temperatures to basically form a liquid out of the gas phase of these gases. There's a big race across. If you read about it, it's very, very interesting because each of them created a big industry. The person who discovered how to make liquid nitrogen, if you go look outside Phillips Hall, the truck that comes in to fill the huge liquid nitrogen tank, that company was started by that person who discovered how to liquefy nitrogen, right? So that company still exists and doing great business, So other than the scientific goal, there also was obviously huge payoffs in doing this. So one of the things that was extremely difficult, one of the gases that was extremely difficult to liquefy was helium. And helium it comes in two varieties, right? Helium-4, and there's an isotope of it, which is helium-3. Helium-4, helium is the second element in the periodic table, right? That means it has 2 electrons, right? So 2 electrons and 2, in the nucleus now, it must have 2 protons too, right? Just for charge neutrality, and then the number of neutrons is up to the stability of the nucleus, but so it can have 2 neutrons in which it is helium, in which case it's helium-4. It can have 1 neutron, right, in which case it's helium-3, right? So there are 2 varieties, 2 stable isotopes of helium. Anyway, so they're trying to freeze helium or to liquefy helium, and that takes very low, 4 point some Kelvin, right? So that's now we know that because before that people had not been able to achieve it. And so they were successful in their group. They were successful in liquefying helium. And once you go to a regime of physical conditions in which have never existed in history before, what do? You measure everything at that temperature or that pressure, right? You measure electrical conductivity, thermal conductivity, whatever physical phenomena you are interested in. You see, hey, is there anything interesting here, right? Is there anything that shows up that was not expected before. And this happens in high energy phenomena. You discover Higgs boson if you go to high enough energy, or this is very low temperature, right? So Higgs boson was expected, but if we look at that point of time, also there was a very interesting discussion because people before that had measured resistivity of metals in great detail, and if you look at the resistivity of a metal, as a function of temperature, if your metal is very defective, typically the resistivity would be low and it wouldn't quite change much with temperature, right? If the metal is extremely pure, very low defects, then the resistivity would typically decrease. And I think you probably know why now, based on all these microscopic theories of scattering and Boltzmann transport, golden rule. Basically, you are freezing out phonons, right? If your defect density is very high, then phonons are not the dominant scattering mechanism. Some impurities are. But if your material is pure enough, you have that. You can. So this is typically called a residual resistivity ratio or something like that. Room temperature divided by some very low temperature resistivity, and can reach, I forget, factors of maybe 100 or so or more in some very, very pure copper or something like that. Okay, so that part is fine. But then what was very interesting is at the lowest temperatures people had managed to achieve, it would kind of flatten out like that. But in some others, it would start going up. The resistivity would start going up. In some metals, it would become flat. And in some others, it would start going up. This was experimentally what was observed. And so there was a, kind of a bit of prediction or controversy, if you might. Some experimentalists and theorists thought it should saturate, and some thought it would actually, who believed a little bit more on the classical side of things, believed that it should become an insulator at the lowest temperatures because, if you think of it as electron gas, you need the heat to have transport, and if you take it completely away, it should freeze out and become a complete insulator. This was there was discussion, and this part was experimentally observed as well, right? So, and later on, it became clear, and maybe this year I'm not going to cover this part of it. The increase in resistivity here is a very, very quantum mechanical effect, and this is related to basically scattering electrons forming closed loops in paths. This is called weak localization, and this was explained only in the late 80s, 1980s, by physicists and others. And what you observe is if you apply a magnetic field, you can bring it down and to flat conditions. And magnetic field breaks time reversal symmetry, meaning a loop like this is not the same as loop like that anymore in a magnetic field. And so that's also a very genuine quantum phenomena. But anyway, so that's not. We are not going to discuss that too much at this point of time. No. That phenomena is very nicely explained by things like Feynman path integrals, which gives you a very simple explanation of why that might happen and things like that. Yeah. Okay, so experimentally, what happened? Of course, that it really for metals you have that. For mercury, for example, right? It abruptly drops at 4 Kelvin, and the resistance basically vanishes. The resistivity vanishes, and vanishes in the sense that the value here, if you want resistivity or R, is really 0. It's unmeasurable, meaning it's not like 12 orders like we did in a MOSFET or something like that. It's really 0. There is no resistance left in many metals, and as there can be some things that some cases which may have some finite resistance. We'll talk about those things later, right? But for most of these kinds of superconductors we're going to talk about, it really vanishes completely. And so that was obviously a very big surprise, which was, as you can imagine, completely unexpected, right? Why would resistance vanish in a metal completely, right? So Now, so basically, those who do experiments, you have to kind of do a 4-point measurement because if, resistance in a superconductor may not be 0, but any electrodes you put on it, you drop voltages there. So there's some resistivity there, right? Okay. Yeah. Any questions? Yeah. So that was the first discovery. But then if you look at currently where we are today, from 1911, 100 some years. So this is the critical temperature Tc, and what you're saying, you have a normal metal behavior above Tc, and below Tc you have a superconductivity. And here's the critical temperature for many, from 1911, which is mercury, the first thing, and soon there was lead, and you can kind of obviously newer materials are being discovered, and one should also not forget that once it's discovered, it stays like that. It doesn't go away, it doesn't go down or anything like that. So so we have now a wide range of materials. These were elemental metals, mercury, lead. Very soon, I think niobium nitride was one of the earliest compound metal, which was discovered to be superconductor. Niobium tin. This was this is actually technologically very important, the niobium tin, because you can draw wires and make MRI and that sort of thing with it. And I think when I was a grad student, one of the conferences I went to in year 2000 was where this was reported. It was a big surprise. Almost 42 Kelvin, and it's a normal superconductor. Basically, people just had missed it. It was around all the time. Nobody cared to measure whether it's superconductor or not. And so I remember there were like 5 or 6 rooms, and the person is presenting in one room, and all the other rooms are video cameras of that room. So a lot of people were very interested in this. Okay, and obviously one of the big discoveries around this time, 1986, 1987, was something that came from the field of perovskites and oxides, complex oxides, which is the high Tc superconductors. They have fundamentally different sort of mechanisms that work to make the resistance 0. We'll talk about those things a little bit later. And much more recently, there are iron selenide. There's a lot of interest there, and if you go to the seminars in the physics or applied physics departments, you will see a lot of talks on iron selenide. It's a relatively new layered superconductor, which I think they can change the superconductivity by strain and all that sort of thing. So there's quite a bit of interest in that as well. And finally, the ones that are reaching close to room temperature are under extreme conditions of high pressure, where you have very high 155 gigapascals for this particular gas. So you kind of make it a solid, and then its Tc is very high. So liquid nitrogen, we have already materials, superconductors, which have higher temperature than liquid nitrogen, higher critical temperature. And then obviously we don't have a room temperature superconductor yet. But it's only been about 100 years. I think, as you know, science, sometimes it may take 400 years for something to come along, right? And but of course, I think I'll also discuss a little bit. But if you think about it, in technology, one of the really biggest revolutions would be if we are able to have a room temperature superconductor. But even if not, it has already led to quite a bit of very interesting consequences. And in that sense, I think looking into the future, a lot of the technologies that are being investigated for, say, qubit-based quantum computation and such, they really benefit heavily from the availability of this set of superconductors already. So things that you just absolutely could not do otherwise. And the properties of superconductors are absolutely critical in doing that. So I will. Okay, so there's a little history, of course, as I mentioned, but I want to kind of start discussing this almost kind of in a historical perspective. So starting from the fact that they were able to liquefy helium, and then they discovered superconductivity, right, in this lab. Okay, so I'll put it here. So they discovered superconductivity, and right after that, within a year, the Camaleonis group had a very, very beautiful experiment I think, as you know, here's the experiment, and I want to kind of start using that to drive how do we understand it today? What's the physical picture we have today for superconductivity? As you might imagine, here's some of the background. Also leans heavily on the stuff we have developed in this course till now, and we'll use it now, right? So, when this was measured, obviously, what approach would one take to explain it, right? What approach would one take to explain it? Before that, you had metals and things that have resistivity, right? And now suddenly that has vanished. So the normal thought process is whatever was causing the resistivity here must be absent here, right? Right. That's the thought process. That I have some scattering rate, mobility, velocity, all that sort of thing. Or going back right the way to Drude model, you have the rate of change of momentum, right? Or rather, force is the rate of change of momentum, right? But then you have delta p over tau, and this is your scattering. That's what leads to resistivity, right? In the end, for example, the conductivity is n e squared tau by mass, right? That's what we have derived multiple times, and mobility is e tau by mass, and tau is how often is the particle electron scattering as it moves through the crystal or the solid. And clearly, if I take tau to 0, I should have infinite conductivity, or in other words, 0 resistivity, right? 0 as tau goes to, right? And I think we also have thought about it as a scattering rate is, in this form, it's proportional to once you sum over impurities and all that, some matrix element squared times some density of states. We've thought of it that way, right? That's tau. So if I make my sample very, very, very pure, if I make this close to 0, this must blow up, right? And so I must get superconductivity then. That's the initial thought process, right? And the problem is it actually doesn't work, because superconductivity is characterized really most dramatically not just by the vanishing of the resistance, but many other things, and just taking this and to 0 is not going to explain any of these other things, So that means this is not the correct approach to the problem. And so that led to the need for a completely new way of thinking about transport in this situation. So it uses still very similar ideas as we have developed, but it's not a diffusive limit. It's not a limit of a diffusive or a scattering dominated transport at all. In fact, what is very surprising is if you make a superconducting metal extremely pure, its superconductivity degrades. It actually needs a little bit of defects also to help you a little bit. It's kind of weird, but it's actually true. So there are defects in these materials. Of course, there must be statistically, you can't avoid the formation of some defects. So your tau cannot, this really can't be 0 statistically, as you know, right? Okay, so this is our original picture, and I will just write. So this is our kind of golden rule result that comes from time-dependent perturbation theory. I'll just write down a couple of relations from time-independent perturbation theory because later on we're going to use it. It's not terribly important. All I want to say, let me just write it down. So if I have, energy levels in the absence of defects, here's an unperturbed energy level. Here are some other levels nearby, E, maybe M prime, and so on. This could be the states of the band structure of a solid. And let's say I put some defects in. I put some perturbation in, and these energies will change a little bit. The energies may float up or down, depends on how they are interacting, what are the matrix elements. So your EU here may change over to some value E here. And that's also given by what's called time-independent perturbation theory. And the way to find that, is basically, here's the result. You can find the new energy level is equal to the unperturbed energy level plus a matrix element of that state itself with the perturbation term plus a matrix element with all other states. So again, this is if you have seen it, great. If not, it's not terribly important. I'm bringing it up right now because it's useful in this discussion. m not equal to u. This is just a formula for how the energy levels change to second order. There are other higher order terms and all that. Any book on quantum will give you these things, and also these are in the notes that I actually did bring that page up. So it's here. So on this page of the notes. So if you want to read it up, there's page 68. Here's the result. So, yeah. And this is the new energy eigenvalue after the perturbation. The new energy eigenstate, the wave function also changes. So remember the states are vectors in Hilbert space, and that will also change a little bit from psi, from the unperturbed value plus a small change, and that small change also looks very much like this. It looks like, well, let's say initial. Oops. All right, so essentially you have a new vector, which is the original vector plus some coefficients times all other vectors it's talking to now. So if the perturbation mixes up these states, that states, these are the terms telling you how strongly is it mixing them, how much is it tweaking this original vector by, and then so on. And the final vector is the sum of all that. Right? So, yeah. Okay, so this is just a basic result, and I'm bringing it up primarily not because we're going to use it today, but just to show that these process, which is these are perturbation theory, is unable to explain superconductivity. Superconductivity is beyond the reach of perturbation theory in terms of explaining it. So everything we have done till now, even things like band structure, transport, and all those things we can explain it by treating the crystal as an unperturbed system plus these little changes around it, right? And the problem with superconductivity is it is not like that. It is a very different kind of phenomena, which superconductivity is not a small change to a metallic state. It is a different phase of the system completely. So as a result, perturbation theory fails to explain it. And when we actually derive the result as to why, what is for example, the critical temperature, you can calculate it, and we'll see whether we can do it today. You'll see that it has no Taylor expansion whatsoever. You can't even expand it. Every term is zero, because it's the ground state of a system, and it has no Taylor expansion and such thing. We'll see that. So, okay. So let's. I just will keep this up here and start looking at some physical phenomena and start to kind of develop at least the notion of what is the physics and how does it. How do we capture, its transport properties? Before I again, one more thing I wanted to add here was, these are the things we have discussed earlier. The last thing I want to say is, if I know the wave function of any quantum state, how do I get from here the current? Right? Maybe you can help me. We have done this, right? We derived this. If I know the wave function, how do I get the current? Yeah.
It would be with the IH bar psi times the
right.
quantum.
Right. So that expression, right, which is we actually get it from the continuity equation, right? That divergence of the current is equal to minus the rate of change of density of particles, right? And that's just the rate of change of the wave function squared, which is the density. Right? So from there, what you get is this expression. But I just want to add, primarily because what happened in 1933 gave a big hint to superconductivity, which is called the Meissner effect. The magnetic field is going to enter this in a big way. Magnetic field and its effect on a superconductor. I'll just say here that whenever you have when you don't have a magnetic field, your momentum operator in quantum mechanics is minus IH bar times the spatial gradient, right? D by dx, or 3-dimensional or 2-dimensional. This is the momentum operator that you can act on the wave function and extract the momentum if it's a momentum eigenstate. But if you have a magnetic field, I think you can probably, I mean, here's the intuitive way to look at it. If I have a magnetic field going like that and I have an electron, we know that the electron is forced to do circles in classical physics, right, around the magnetic field. Okay, so now, so B causes electrons to go like that, right? And I think you can physically see that if I write magnetic field not as itself but as a curl of the vector potential, right, curl of the vector potential, and to have a magnetic field in that direction, the vector potential must curl around it. So the vector potential is going like that. Do you see that? So it's like a cylindrical symmetric, and the different gauges that can give you different, but essentially physically this is what's going on, right? And so now with the magnetic field and the charge, you can think that there is a momentum, or there is a momentum being imparted by the magnetic field to the electrons that's carrying it around like that. So the force, and this is actually correct, if you derive it completely with its full quantum mechanical rigor, you will get that the magnetic field, or rather the momentum due to the magnetic field, is just electron charge or particle charge times the vector potential. This is the particle charge times the vector potential is equal to the effectively the momentum. You can think of it in many ways, like impulse or things like that. You can think, but essentially this is what enters, and the net momentum operator then also must include. It must. So I think plus Q plus E. Yeah. Okay. So it must also include. This is actually charge. Any charge, not just electrons, but any ion, whatever be it, right? So here you must then include. So the way it enters here in the momentum operator is it is added on to the normal mechanical momentum, if you might, right? So this is a vector potential based momentum. This is a normal mechanical momentum, and for an electron, this just becomes charge is negative of 1.6 times 10 to the power 9. So I'll just write it as this E times A, meaning what do I mean by that? Q is the electron charge is minus E, and E is just positive. I think it's all sign convention, just like that. So E is positive, 1.6 times 10 to the power minus 19. So this is your momentum in the case you have a magnetic field. And the reason we are talking about this with superconductivity is because that will have a very drastic effect on superconductivity, which none of the perturbative theories can explain. So, and once you have that, the net expression for the current, and I'm going to not try to derive it, but I think you can do that, and it's also done in the notes. But your current density in the presence of a magnetic field is given by very similar expression as we had done earlier. So if you know the wave function, it gets times minus. Let me write that down properly. Psi star minus IH bar times gradient, right, of psi, minus the other way around, flipped around, right? So over twice the mass of whatever quantum state you're looking at. This was the expression we had before, right? But then there's an additional term that enters here because of this vector potential induced momentum, so, right? Vector potential induced momentum, and that term has actually the charge, electron charge in it. When I say electron, it is whatever charged particle you have. Just to be careful, because in a superconductor you may have a pair, so it may be 2 times E, Cooper pair, for example. And E over m, which is the mass of that, times psi star psi times the vector potential. So that's what you have here. That's the total current. So the current is actually proportional. The quantum mechanical current is proportional to the vector potential, linearly proportional to the vector potential. And physically, hopefully, it kind of makes sense that this is the vector potential that's driving the current anyway here, right? In this situation, for example. So yeah. Okay, so that's one more expression that we have derived earlier, and this expression is good enough. It doesn't need any modification, and it will explain a lot of things about superconductivity. This is a full-blown expression. It doesn't need any other approximations. Yeah.
How come we can add an electric field as a perturbation, whereas we need to incorporate the magnetic field into?
Yeah, it's a good question. Good question.
Is that just a classical mechanics thing that I haven't thought about in a while, or is that something different?
The electric field is a good question. Electric field is already taken into account in finding the psi. That's what we are thinking of it in that sense, that the field, the internal fields that you have inside the crystal, or even any external field applies, can already handle here. Or another way to look at it is in the problems we have looked at till now, electric field, what it does is it doesn't change the size, it changes the occupation functions of the K states. So the two is to look at it, yeah. So you could, of course, include the vector potential from the very beginning too. But given that we are saying that if I did not have a magnetic field, and this was my state, if I turn on a magnetic field, now what happens? Now this is what I'm saying is this is still complete. This takes into account of what happens in the presence of a magnetic field. So yeah. Okay, so and I think from here we have also discussed earlier that the wave function, you can't have a current in a bound state, of course, as you know, and in a bound state the wave function is real, so these two terms just cancel in any real thing. So bound states have no net current, and the wave function must have some complex quantity to be able to transmit current around, some from one place to another and all that sort of thing, or even in a loop. Okay, so let's go back to the experiments now and start seeing why is it that it's very, how did people piece together the story? And it took almost half a century for people to explain, the phenomena from both from a qualitative picture as well as the quantitative microscopic picture. Both, even the qualitative picture was, so it really was a for some of the people who developed quantum mechanics and crystal theory like Bloch and Bohr, they had it was very difficult to explain superconductivity primarily because many of them were approaching it from this path, whereas it was later shown that it's not possible to explain it that way. It's not a perturbative phenomenon. So okay, so now let's go look at some, and then you will see here. Very interestingly, every time there is any new experimental evidence, the theory suddenly improves and you find something new in it, and so right after the discovery of superconductivity, the vanishing of resistance is obviously extremely striking and rather remarkable, and it's extremely useful, of course, for many things we use, electronics and lossless transport of energy and that sort of thing. But what we'll see is that's not the defining feature of superconductivity. The defining features will come one by one. So one of them is a persistent supercurrent. So what is a persistent supercurrent, right? So persistent supercurrent is and this was what was done by Kamalegones right after they discovered superconductivity, that if I take a loop, if I take the superconductor and I make a physical ring with it, and then in the loop, and we'll discuss this how, I'm able to create a current flow in the loop, right? And then whatever created that current flow, I take it off now, right? And let it sit, right, at its superconducting state. The question was, if there's a current flowing, how long is it going to flow, right? How long is it going to flow? Will it decay with time? Will it survive for a long time or not, right? And I think, as you can see, if it's a superconductor, it probably should hold steady for a very long time, right? It shouldn't decay. How do we picture this? For example, if I look at current in such a classical, if I look at current in a loop like this, and I set up a current at time t is equal to 0, which is a certain amps or amps per centimeter square in a metallic loop at room temperature, and I let it go, it is going to decay. So meaning if I leave it unperturbed after that, after I turn it on, and it will decay with a certain time constant, e to the power minus t by tau. And if I just have a metallic loop carrying a loop current like this, That time constant is also very well known. It's basically you have a resistance because of scattering inside this region, right? And because there's a current going and there is a magnetic field generated, there's an inductance too. It has a self-inductance. This object has a self-inductance and it has a resistance. So there's a resistance and a self-inductance of this loop, and they combine together to form a time constant tau, and the tau happens to be, I think you probably know, it's just L over R. That's the time constant. Just like RC, here it's inductance and resistance, right? So inductance over resistance means the resistance will go to the numerator and inductance will go to the denominator, and that's how it should decay. That will tell you how many milliseconds or hours or whatever this current will continue flowing before it decays to zero, right? So this is the picture. And so when experimentally this is done for a superconductor, what is found is basically it just does not decay. It just stays constant, and of course you have to make sure that it remains superconducting, right? And but then if you do, I think people have already measured for many years. The current keeps going, but now if you estimate or project, I think some of the projections go to be like 10 to the power 20 seconds, which is larger than the age of the universe. So that means that is forever, right? So that means that thing really, the resistance, that what it really implies is this inductance is very finite. Inductance is very finite. You can calculate what's the mechanic, from classical electromagnetics, how much is the L. So the R really must be really zero or extremely, extremely small. So that's what it's saying here, right? But there's actually something more than that. So the question that bothered people for a rather long time is why is it not only not decaying, it actually does not change at all. It doesn't even droop. It just, of course, the R, from this picture it's clear why it should be, right? But if you try to bring quantum mechanics into this picture, you'll see that it's possible for it to go through discrete steps to zero instead of going through gradually. And it just doesn't do that. And the reason for that is actually very much it's actually protected by topology. The fact that we'll see that when it's a topologically protected current transfer. It just cannot, it has no way. So we'll see there are two factors here. There's a phase of the wave function of the electrons, and then there is a amplitude, and neither one of them gives you any opportunity to change at all. It's very resistant to change. We'll see that very soon by just applying some of these things we talked about. So persistent superconductivity, we'll come to that. But the next thing is electronic specific heat of these materials. And what does that mean? Specific heat is what is the meaning of specific heat? If I take a solid, right, and I heat up, I give it a certain amount of energy, the question is how much is the change in temperature of this solid? That's the physical meaning of specific heat. Specific heat of a solid will be typically, if you look at metals, it looks like something like this, right? It has a part, it has a TQ part and a linear part. TQ part is due to lattice specific heat because of the atoms, and this is due to the electrons themselves, right? Free electrons or mobile electrons, whatever be it. So there are two parts, lattice. As I think the heat can be, the energy can be sucked up by lattice vibrations or by electron motion themselves, right? And there are the two kinds of particles here. And so mathematically, the specific heat goes as, the definition of specific heat. Let's just look at the electronic part. It's how much energy you give divided by what is the change in temperature. That's the meaning of specific heat. And if you measure a normal metal, the specific heat looks like this. For lattice kind of dominates. It goes as TQ. And then, of course, at some point it goes superconducting, let's say. But when it's superconducting, the lattice part of the thermal conductivity vanishes. This is the resistivity, And here we are plotting the specific heat. And this is kind of the electronic part of the specific heat, just this part. And above the critical temperature, in which is a normal metal, it's going as linear, here. And we can explain that in a couple of lines, and we will. But below, it's very interesting. It has an abrupt jump in the specific heat for electrons, and then it goes down like that. And if you do this properly, experimentally, if you do the experiment properly, you see this is exponential. So the specific heat goes exponentially with temperature. And whenever that happens, the reason that happens is there is a gap in the energy spectrum. The energy is allowed for whatever particles are in there. There is a gap, just like the band gap of a semiconductor. There's a gap here, and this gave the first hint that superconductors, even though they're metals, I think we know that in a metal, near the Fermi level, there is no gap. I mean, that's why it's a metal in the first place, right? But what this experiment is saying, once you go from the metallic state to the superconducting state, somehow a gap has opened near the Fermi level or Fermi surface. Why is that indicative of a gap? Because let's see. I mean, why do we get a linear specific heat? Because I think in a metal, if I look at the energy and the number of electrons at any energy, free metal. So you have a band. And let's say a three-dimensional metal, the density of states is going like that. And you have a Fermi level somewhere here, right? And these states are filled, right? And now you're giving it energy in the form of heat. If your energy you're giving is kT, if you have heated it up to a temperature T, then the electrons can only take energy is kT, right? From the external heat source. And I think you can see immediately all these states are ruled out because they're completely Pauli blocked. Those cannot absorb kT and go here. The only ones that can are within a small window of kT near the Fermi surface here of the highest energies. Only those electrons can absorb that heat, right? These are unable to absorb because of exclusion principle of electrons. And therefore, if you just look at how much energy can be actually absorbed, what is the numerator, how much energy can actually be absorbed by the whole population of electrons, what you realize is it is basically proportional to kT over the Fermi energy. I mean, in some, maybe there's some power, but you can see that this window divided by this whole window, that's the rough fraction. And it's like 3/5 or 2/3 depending on dimensionality, but this is the temperature dependence, right? This fraction of electrons can absorb, and each of them can absorb roughly kT, right? So now you see you have a t squared, and you take a derivative, and you get it's linear with t. So that's how you get this term, right? So it's just electronic specific heat is proportional to temperature, right? And that's true, and experimentally you can measure it. By the way, this part is relatively small compared to the lattice thermal conductivity, but it can still be measured, and this is where it is. But the moment you actually look at, or rather when specific heat was measured for superconductors, you can see it has this sort of activated behavior, and there's a gap associated with it. And if there's a gap associated with it, then the number of electrons, well, we'll see later what happens is there will be effectively a gap, but not in the single particle spectrum. We'll see it's in a many particle or Cooper pair spectrum, not in a single particle spectrum. The main point here is that if you have a gap, I think you know that the number of particles is dependent exponentially on the gap, right? Number of particles you can have excited across a gap. If a gap is delta, then the number of particles, so let's say this is filled. What do we mean by gap? These states are all filled, these states are empty, and there's an energy gap between them, right? That's what we mean by gap. And at a temperature T, how much of them are excited here? That is always e to the power minus del over T. That's kT, right? That's roughly how much is excited. And now, instead of writing it in this way, kT over EF, it should really be in the form of e to the power minus delta over kBT, right? You can not kT by EF, but an exponential e to the power minus delta by kT. And you can take this now, take its derivative, and you'll see you can completely recover this form of the electronic specific heat. So I think there's nothing simpler to plot, so I can make a plot of that. So I'm just going to see. So here, it just looks. Here's a linear term. Here's a superconducting term or a gap term. Right? So it's a very simple plot, right? It's just the formula. Okay. So now, so that's hinting at the fact that there's, though it's a metal, above TC, when it goes below TC, somehow there's a gap somewhere. It has gone from a metal to something that has a gap, and we know that if you have a gap, it should be an insulator, but actually it's a superconductor. It's the exact opposite. Right? So that's very strange as well. Right? So, any questions here? I can wait if you need any explanation. Yeah. None? Okay. Yeah?
So this gap is in the available electronic states.
Correct. So essentially, it's a gap in the energy spectrum, right? So and basically here we're talking about energy, and yeah. So it's the an energy. It's a gap in the energy allowed energies.
But this would not be the band gap you calculate, but the band structure that we went through for XAML.
Just like the band gap of a semiconductor is also, valence band, conduction band, it's also a gap in the energy spectrum of the crystal. And electrons can have, energy still here, let's say, and then none here, meaning you have run out of electrons, so now there's a gap, for example. Right? And this is really no different, except the energies here are single particle, just one electron energies. We'll see later on when we discuss, we haven't discussed that yet, but that energies would be that of Cooper pairs or paired electrons, not single electrons. We'll see that. In other words, what we'll see is you cannot explain superconductivity with single particle physics. It's impossible to do that, and they form a condensate or of many things. So, yeah. Okay, so the next thing is one of the biggest experimental advances was the next one, which is the Meissner effect. And the Meissner effect, just look at this, it took 20 some years for somebody to do this experiment, and that really opened up a little more understanding of superconductivity. And the Meissner effect is very simple again. If you take a superconductor, so it was discovered by Meissner and Ochsenfeld, I think but it's referred sometimes by just the Meissner effect. If you take a superconductor and if you are normal metal state above the TC, normal metal state, and you apply a magnetic field externally, and the magnetic field will go through the metal, and it behaves like a normal metal. There's nothing fancy about that. But if you now keep the magnetic field on, and then you freeze the superconductor from the metal and go below TC, and it goes into superconducting state now. Right? So now what happens is if you are sitting just on the outside of here with a magnetometer and you're measuring the magnetic field, you'll see the magnetic field increase. And what happens is the superconductor expels all the magnetic field from its interior. It just pushes it out. And then that's called the Meissner effect, that the expulsion of the magnetic field from inside the superconductor. It cannot sustain a magnetic field inside it. And the expulsion of the magnetic field to many people is actually the more defining feature of a superconductor than the vanishing of resistivity. Well, both of them go together, but this is actually a very important effect, and we'll now discuss a little bit about how that is explained. And so basically just a couple of years after that, two brothers actually, Fritz London and his brother, they were able to give a classical theory of why this might happen, classical theory, but not still consistent with, not yet a quantum theory, and that took till 1950s for Landau and Ginzburg to come up with a new idea of explaining it, and I'll go through that today. Landau-Ginzburg theory, and then, but still Landau-Ginzburg theory was completely, didn't say, it's a qualitative theory, or it's a phenomenological theory, which makes it extremely powerful. It can't be wrong, because it's completely, doesn't care about what goes on microscopically, and it just explains why is it so stable, why is it superconducting, how can you explain all these parameters, specific heat, or vanishing of resistance, infinite supercurrent, and all that together in one shot. It can explain those things, but it doesn't tell you what should be the critical temperature. It doesn't tell you the microscopic details. That was given for that too. It took another experiment. Initially, Froelich, from his theory of electron-phonon interactions, had an idea of why there might be a gap, why might there be some of the phenomena that was being observed. And then right after Froelich's theory, there was another very important experiment called the isotope effect, where superconductors with different masses of atoms, same atom but different masses, essentially different number of neutrons in the nucleus were measured, and the TC was found to shift. So that gave some hint about what is the origin of superconductivity. And combining all the stuff before that, the microscopic theory was created around 55, 56 by Bardeen, Cooper, and Schrieffer, and that is currently one of the most celebrated theories of superconductivity. Just to be clear, BCS theory tells you how to calculate some of the parameters and such things, and it also tells you why electrons might pair. But many of the other features are really explained very clearly by the Landau-Ginzburg theory. Things like why is it topologically protected? Why? So that many of those other things are explained by Landau-Ginzburg theory, and that gave birth to quite a few. I mean, these ideas gave birth to spontaneous symmetry breaking and all these things that led to. It's been used by many fields now. Particle physics and all that. So many of them originated here in the superconductivity area. So. More recently, I mean, there's obviously high temperature superconductors, and there's still quite a bit of work on trying to understand its origins. I think there's some conflict in what theory is exactly right. It looks, there's some progress being made, and more recently there are potentially new forms of superconductors which have unconventional topology that in them are also being looked at. I think there's one project you are going to look at some aspect of it and present that. Okay. Okay, so let's delve a little deeper now. Let's look at the physics of using some of the things we have developed till now to start building together a consistent theory for superconductivity, and we will start with our expression for the current, which we have, which I said is actually still correct. We don't have to change anything there. I don't know where it went now. Right? Yeah, there it is. Already filled up the space. So okay, so here's the expression for the current in a superconductor, and what we want to now understand is why is it that when I have a magnetic field, it's being expelled by the superconductor. I want to see why. Why is it getting pushed out of a superconductor? Right? And this will give us the answer. But at the same time, it will also give us the answer as to why, if I have a superconductor, the current keeps going. Why is it topologically protected? Why can't you change it easily? So that's something. It will also give us that answer. And both these answers will depend on something that Landau and Ginzburg did. They gave us a wave function. They basically guessed it, if you might, but not guessed it. I guess they looked at all the phenomena and said, what wave function can explain all of it? That's how it started. That's how they and then here's the wave function, and you will actually like it because it's very, very simple. And does anybody know what it is? The Landau-Ginzburg wave function? Yeah, it's very simple, right? Yeah, maybe you're doing the project. You better know. What's that? Exactly right. So the wave function. Remember, we have looked at wave functions of electrons as e to the power ikx and all that sort of thing, right? Earlier, plane waves, that sort of thing. But the wave function of this situation is actually very interesting. Here's the wave function for that Landau and Ginzburg came up with. That psi of r is equal to some amplitude. Just I'll write it down first, and you're like, okay, there's nothing new there, right? But let's just look at it carefully a little bit. Okay, so this is the wave function, and of course, every wave function you can write it like that. There's nothing fancy about that at all, right? But here's the catch. This is the wave function for all the particles, not one, but all the Cooper pairs together. It's a macroscopic wave function, meaning this is the wave function for if I have 10 to the power 20 Cooper pairs, they all have only one wave function because they all form one system now, one quantum state, macroscopic, it's like one atom, right? If you look at the S state of one hydrogen atom, it has a wave function, right? If you have another hydrogen atom there, that has another wave function, right? But this is not that kind of thing. If you have 10 to the power 20 Cooper pairs, this is the one single wave function for all of them together. It's a coherent state, of all of them. That's the major difference. Does that make sense? I mean, this is a many-body wave function, and all the bodies are individual Cooper pairs, and they are in some sort of a phase. If they're located at space r, and their phases, the whole object has a phase theta of r that can vary in space, and it has an amplitude of this much that can also vary in space. So many-body wave function. Okay, so and that's clearly a big change because before that we have always looked at individual k states and wrote down their wave functions and summed over all k states here. In the superconductor, there's no sum to do. You just know the whole wave function and you just find the current right away. There's nothing to sum here. Right? Does that make sense? I mean, that's the weird part of the superconductor. Yeah.
C of r is equal to the absolute value of C of r. Those aren't the same thing, right?
Say it again. C of r.
Your psi of r
the wave
is
function.
equal to absolute value of psi of r. It's not reciprocal, right? Oh, it's a capital psi of r on the left side.
No, they're the same thing. I mean, I'm just saying here's the amplitude and here's the phase. No, they're the same thing. They're the same thing. This could well be a single particle wave function, but I'm not trying to say that Landau-Ginzburg's idea was it's a macroscopic wave function for all particles that are contributing to transport. They did not know about Cooper pairs because they were a few years before Bardeen, Cooper, and Schleifer, and the Cooper pairs came later. So yeah, is that clear? So now, if you take this, and you can throw that in there and say, okay, now what's the current, right? What's the supercurrent or superconducting current that will flow here? So let's do that. In fact, let's make it even simpler. Let's look at what is, if I take psi star psi, right? I get, mod of psi r squared. The phases cancel out. And physically, what is this then? Physically, what is psi star psi in quantum mechanics? Right? It's the particle density, right, at any point r. So this is basically your electron, or whatever particle it is, density at any point r. Right? Psi star psi is the probability density, right? In fact, let's make it even simpler and say that that thing is my amplitude is not changing in space. Let's say that and in that case, I can write my wave function. If the amplitude is not changing in space, then the wave function is even simpler. The macroscopic, at least, wave function is square root of the carrier density, which is, I'm assuming, uniform everywhere, times e to the power I of phase, which is changing in space. The phase is what's changing in space. And remember, there's only one phase for the whole object of all these, large number of particles that are going to have superconductivity, just one phase. And so this is just a simplification. You don't have to make this, but it makes whatever discussion we're going to have, it makes it a little easier now. Right? So, and if there are any questions, please interrupt me and ask. So we just made this simplification, and then you can start putting those terms in there and see what it gives you. Right? And what it'll give you here is you can see the gradient term is going to give you a gradient of the phase because there's no gradient of the amplitude. It's not changing in space. So you just get a gradient of the phase. And this term will just give you a linear term. Let's write that. That's the easier one. E over mass times the electron, or rather, not, I shouldn't call it the electron, the particle density, whatever particle it is. Just that times the vector potential. Very simple, right? So that's the contribution of current due to the magnetic field. Right? Or the contribution of current due to this part is let's write that. So you get M. So by the way, I should be a little careful. Don't. This is not the charge current, this is the probability current, you know what I mean? So you have to multiply this by the charge to get the total current. This is just the probability current, even though there's a E sitting here. Remember, because E times the vector potential is the momentum here, the charge. So that momentum of the particle is dependent on its charge, actually, yeah. Okay, so the probability current then. From here, what you would get is again, you will get a carrier density dependence clearly, right? Because there will be a psi star psi and n, and you get a h bar times the gradient of the phase of the state over. Actually, what you'll get is from here you will get both the terms will be the same, and so you get 2, and that 2 and this 2 will cancel. You get just n over m like that. You know? And so you can now take all these things common here, and let me just write that n over m h bar this plus the charge times the vector potential. You know? So that's your probability current for a if here's the only thing we have done. If this is your wave function, that's the current, right? According to the all known laws of quantum mechanics at this point. So okay, so now so by the way, this is a vector, right? And you see physically it's very interesting because this part of the current is easy to understand. This part is being moved around by the vector potential, but this part is dependent on how is the phase changing, phase of this whole macroscopic object. How is it changing in space? That's what this depends on. Now phase is a very interesting term because it can have you can go around loops, but when you come back, it need not be itself, but it should be off by 2 pi. As long as 2 pi times an integer, it's okay, I mean, because e to the power I, it is single valued. The e to the power I theta part of it is single valued, meaning if I change r along some path and I come back to where I was, as long as the theta is theta plus minus 2 pi times an integer, it's still fine, right? So it can change, right? And that actually will have a very interesting effect. That will tell you why it's topologically protected very soon. Yeah. Okay, so this is your relation, and let's first look at a situation which is just a normal superconductor, not in a ring, but just in a normal superconductor. Here's the way to explain how the flux is expelled. Let's say my phase is also constant everywhere. The phase of the of the macroscopic wave function is also not changing in space, let's say, right? And I do have a vector potential, I have a magnetic field, and I have a situation like this now, right? I have inside the material, I have created a situation where, so essentially if my gradient of the phase term goes to 0, and I'm looking at a situation where I have a magnetic field, so J of R, let's actually look at the total current now. Right? Total current is whatever charge you have plus that will be the charge, and we are writing E as the charge. It could be 2 times electron charge if it's a Cooper pair. It's just E. So we're just writing it as like that. So I have E n over n is the particle density over the mass, right? And then you have another E from the vector potential. We're saying that let's see what happens if the phase is not changing. Phase is also spatially uniform everywhere. In which case you have E squared n over m. There's an E here and there's an E there, n over m, times the vector potential. Right? So that's your current now. Or Ne squared by mass, electron density, charge squared by mass, and times the vector potential. So it's actually a very weird result, and this is essentially getting close to the London theory now, which is which explains why magnetic field gets expelled from this material. Okay, so that's the current, and I think you also know that from classical physics. Actually, before we go to classical physics, you can take. I know that in class, EMAG theory or Maxwell's equations, one of the equations is Ampere's law, right, which relates current to magnetic field, right? Like a Biot-Savart law. If you have a wire carrying a current, what magnetic field does it generate, and such things, right? So yeah.
Wait, why did the gradient of the phase change function look zero?
I have not justified it. I've said that let's make that simplification at this point and see what happens if this goes to 0, right? If the phase is not changing anywhere in space. In that case, what happens? Let's look at that first. Then we'll recover it. We'll bring it back soon, right? So, okay. So we know that from Ampere's law that the curl of the magnetization, right, is equal to the conduction current in any material, right? That what we know. And then there's a displacement current, but we are not talking about that at this point. Inside material medium, and that is basically magnetic field over mu naught, which is the permeability of free space. So that's your relation that we know, right? And so here you can see now that is this correct? What I did here? J is NE. Yeah, that's correct. So, by the way, here, if you want to kind of also one more thing I want to add here was if you want to make some sense of how is it, you can see that E times the charge times the vector potential is acting like a momentum because you have n times electron charge times the velocity here. You can see that. I just wanted to point that out. And you see the velocity is the charge of the particle times the vector potential by the mass. So that must be the momentum, right? So that's the physical connection here. If you want to relate it to our older picture of transport and all that. Okay. So right. So here we also know that how is B related to A? Right? Maybe you can tell me that. That's just the curl, right? Curl of the vector potential as we had. Okay, so the curl of the vector potential physically also, it's the loop around the wire, for example. Okay, so I want to kind of get rid of say the vector potential here. So for that, I must take a curl of both sides, right? And then I can just use the magnetic field on the right side. So that just gives me a magnetic field. And this is basically the London theory of the Meissner effect. And the curl of J means, unfortunately, I have to take a double curl here, right? So that gives you what is the curl of J is equal to mu naught times curl of J, right? And I think curl of curl, again, this is, I think I've been in the field too long now that I remember this, but so it's a gradient of the divergence of a, minus the Laplacian, that's how it looks. This is the identity, curl of curl. So, okay, and divergence of magnetic field, at least we know no monopole, so we'll take it to 0. Magnetic field divergence is 0. We'll have some more things to say about that later on in the course, but at this point it's 0. So it's mu naught times curl of J. Anyway, so you can take this now and replace all that stuff here. Curl of J is that over mu naught. I think here, just to be clear, I think I missed a negative sign here, and I'll explain why. Okay, so here's the charge, but then when I multiply it with the, we can go back and check it. There's a negative sign here. I don't want to kind of spend too much time on that and say I get the Laplacian of a magnetic field over mu naught is equal to that, and I can take the mu naught there. Anyway, I get this expression now. I can now remove my minus signs, and this is your relation now. It's an equation in the magnetic field. Okay, so in space, it's a gradient, del space derivative in space. So you can see that this whole thing here must have units of 1 over some length squared, right? Because it's d by dx squared here. This must have some units of 1 over a length squared, and that length squared is called the London penetration depth of the superconductor. You know, how far into the superconductor does the magnetic field penetrate into the material? And let me just write that down. That lambda L will be m over n e squared times mu naught square root. I think that's what we got. And the idea here is the magnetic field will either increase or decay exponentially, because that's the solution, right? d2x by dt squared. So the magnetic field as a function of, say, length will go as magnetic field on the surface of the superconductor e to the power minus x over lambda L. That's how it's going to decay inside. Yeah. Let's just look at the thought process a little bit, that if all these conditions that we talked about, if Landau-Ginzburg theory is correct, I have macroscopic wave function. If I make the assumption that my phase is not changing in space, then the magnetic field should decay inside the material, right? And experimentally, we know it decays inside the material, right? So let's go back and look at the phase and all that. We'll kind of discuss this back and forth now, but at least it's clear that this part should be clear. Right? And from here, you can also write down what should be the current, because we have the J here, and you can. I think we know the current is just that expression there as a function of magnetic field. So physically, what is going on here, right? So let's look at physically. What's the picture? Why is it expelling the magnetic field? If I have a piece of superconductor like that, right, and oops, sorry. And then I have a magnetic field applied. If I have a magnetic field like that, I can sketch a few things. I can sketch as a function of the distance, let's say from the center towards the radius of this. Right. So if I have a magnetic field going that way, I think you know that the magnetic vector potential is going around like that. It's circulating around, right? The vector potential is doing that. Is basically some aid of angle phi, if you might, around the cylindrical axis. Okay, so what we do know is outside, very far away from the material, the magnetic vector potential is probably magnitude-wise. Well, I don't want to kind of sketch it, but it has some value, So if it's uniform, it's probably constant everywhere or something like that, right? So, but what we are seeing is as we go into the material, if your magnetic field is decaying, so is the vector potential. So everything essentially decays, just like electric and magnetic field all decay inside. So if I plot this inside the vector potential, this is essentially going to decay like a London penetration depth. And if you plug in the numbers of typical Planck's constant, no, not Planck's constant, but particle density, Cooper pair charge, permeability vacuum, mass of the Cooper pair, your number would be like 50 nanometer, 100 nanometer, 10 nanometer order of magnitude, tens of nanometers, not meters or microns. It's tens of nanometers. So that's how far deep inside this field penetrates into the material. And as I was trying to say, you can think of it as either as the B or the vector potential or whatever. It decays like that. Right? And now you can probably see what is physically going on by going back and looking at all these assumptions physically, right? So as the vector potential decays, right, inside, the phase must change there. The phase is going to pick up some, right? And what is physically what's going on is if you look at the expression for the current itself, the current is some constants here, NE square, mass, and all that, times the vector potential, and there's actually a negative sign in front. And physically, if you have a vector potential going that way, the current actually flows in the opposite direction and a very thin ring outside the material. And that really protects the interior of the superconductor from the magnetic field. That's what stops the magnetic field. So essentially, as the vector potential starts decaying, the phase part kind of picks up, and the phase term, inside that region, it actually, because there is a particle current flow because of that, and they will cancel, and help expel the magnetic field from inside of the material. This is one way to think of it. I've obviously made that assumption. You don't have to. You can start without making this assumption. But going back to it, you can see that if I change the magnetic field, how will it respond? It must change the current that flows around on the surface of the superconductor, only on the surface within a skin depth, or within this London penetration depth. This is a thin ring outside. Yeah.
I don't get how this is unique to superconductors.
Yeah. So it's a good question. So in a normal metal, if you have a constant magnetic field, the magnetic field will go through the metal, and there will be magnetic flux lines that will be inside the metal, right? It's only when you change the magnetic field that you have this skin effect where the currents flow and the eddy currents outside. Here, this is a DC phenomena. Even if you hold it without time change, so that's physically different from a normal metal. The magnetic field lines in a normal metal or semiconductor or any insulator, the magnetic field line goes through it. There's a magnetic field inside the material. Here, the magnetic field is expelled because of this reason here. That's what I said.
Okay, but like what intrinsic material property does this term stem from?
Good question. So we haven't really discussed that yet. What we have only invoked is that where did I write land? Well, the wave function. There's one wave function for every particle. That's what has led to this.
Okay.
If I take that out of the picture, it'll be very difficult to explain all this stuff now. And that's a very strange assumption, right? But that's what's able to explain all this. By the way, London theory, that when they explained the Meissner, that was way before Landau-Ginzburg. But I'm kind of jumping ahead in time a little bit, also brought in the microscopic picture. But you don't have to talk about the wave function yet, almost. I mean, as long as you make an assumption that the current is minus this, right? And there's only one object, a macroscopic object that's moving, not 10 to the power 23 individual per centimeter cube electrons, but just one thing. You can, that was the London theory. They said that it's one macroscopic object, it's like an atom, just one state that's rotating. The whole object is rotating rigidly, rather than like water flowing where water molecules can collide with each other. The whole it's like a solid object that's rotating. That's the physical meaning of it. Yeah. There was a question? No? Okay. All right. So so this hopefully gives you some sense of where this comes from. But let's now look at the persistent current around rings, because that will also be explained using. Well, by the way, you can see that this is the most general formula now for current flowing in a superconductor. One piece of superconductor, be it in a ring, be it in a thin film or whatever, right? Okay. So now, once you put it on a ring, there's something very interesting now, that the phase cannot be anything you want anymore. The phase, once you have a ring, has to satisfy a certain criteria. And this point I want to emphasize a little bit, because the next topic will be topological insulators and all that sort of things, and this point will be invoked again and again. So, and I think they were all preceded by the superconductivity theory anyway. Okay, so here let's say now our current is going around the loop, J of R, and we have that is the expression for the current. Let me rewrite it here. H bar times gradient of theta plus the charge times the vector potential. All right. Okay. So now we're actually looking at it from the other end of the spectrum. Here's the experiment. Okay. So how do you physically create a current inside a loop where there are we can't put a battery here, right? So it's closed. So how do you create a current here, for example, physically?
Induction.
Yeah, induction. Physically, what do you do then? That's correct. Yeah. What's that? Another loop, you're right. Or yeah, I mean that's correct. Another loop, and or you can think of it as basically a magnetic field, right? You have a magnetic field. you have created a magnetic field, and at time t is equal to 0, you shut it off, right? So the magnetic field was rotating the carriers around classically, and then at time t is equal to 0, you turn it off, right? And when you turn it off, if it's normal metal, it will decay, right? The current will go to 0. Basically, well, the answer is basically a magnetic field is what you need to move current around a loop, right? It's very simple. But the question we are asking now is at time t is equal to, so let's say I come across a loop like that, and there's a current flowing now, right? So, and I measure experimentally, and there is no magnetic field anywhere, right? Right. What does that mean? That means this term is 0, right? So that term is 0 now, but there's a current flowing, so that must mean that there is a gradient of the phase around, right? This is the term that's doing the heavy lifting for the current flow around the superconductor now. Yeah. And so if it's a persistent current and you measuring that, so your persistent current will be, E times Planck's constant now times the carrier density over mass times the gradient of the phase. And what physically this phase, you can see now, that's the phase of any point inside this loop. If you go here, 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 that's the phase inside at every physical point in space, right? Inside the superconductor, and that's the phase of the macroscopic wave function. I think it's kind of so. All right, so so the word macroscopic may seem very, actually it was not very clear when Landau and Gisberg proposed it. What do we mean by macroscopic? What does that actually mean? Physically, what it really means is, as I mentioned earlier, there's one wave function for all particles in this loop, whether it is, 10 nanometers in diameter or 50,000 kilometers. It's the same deal. If it's a superconductor, that whole thing is one wave function, and the phase is the one wave function for it. So that's the current density now, and I think you kind of, if you look at it a little carefully, you'll realize now that it has some this phase cannot just have any value. It cannot have any value. The phase must have this criteria that if I found the phase here, and then I go around the whole loop and I come back to the same point, right? If I come back to the same point, then remember the phase is now a function of where I am. You can think of it as an angle, and then maybe the angle with this vertical axis, and then inside this maybe a circular cross section. You have a certain R. You can kind of go around this circle and then see. You can sample the whole space that way. And the phase must satisfy that if I take the phase, or if I take this quantity, gradient of the phase, right, and I go around the loop, right, and let me just write it here. So the wave function is, I'm saying it's square root of n e to the power I theta of r, right? And if I go around a loop, if I increase the r by a certain length, and I come back to where I was, right, then theta of r must have changed, because this hasn't changed. And what I'm trying to really get to is, if I translate r plus l here, the theta of r plus l should come back to 2n pi plus theta of r, right? It should come back to this value, right, once you have the loop, right? And that's just the wave function, right? Let's look at the current. So for the current, current has the gradient, and you know that if I take the gradient and I try to integrate it around a loop, closed loop like that, whichever path I choose, I can choose either a linear path through the center of this axis, or I can choose a winding path which goes around in loops like that, right? Do you know what I mean? So I can choose any path around, right? Inside though, right? That clearly is essentially an integral of d theta around the loop, right? And what actually it calculates is how many times is the phase if I get it to be m, times m times 2 pi. Okay, so m is an integer, not the mass, but that calculates how many times is the phase winding around, this loop, and it has to be an integer to come back to where it was. If it wraps around, like that, or if it goes straight, it can be 0. It doesn't go around the center once. But if it does any sort of winding, it must come back to an integer times itself. So, that's very interesting. Why? Because if you look at the current, it's saying that the current, if we were to change, it cannot change by continuously. It must jump from one value to another. There's an integer part hanging out here. And that's actually kind of very interesting. And if you look carefully, you will also notice some other aspects of this. It's got to do with, I'll come to that later. In a flux quantum, if you have one more, the current will jump by one amount and 1 unit and that sort of thing. We'll come to that later. But essentially, here's something that we are trying to explain now. Why is the current? Why does it not change over time? So again, for the current here, you have the wave function, the electron density part and the gradient part. And we are seeing basically that the gradient of the phase is resistant to change, primarily because it has to change by a very large amount, to be able to change your current, to decay or something like that, right? If that can't be taken to 0 gradually, clearly it cannot be taken to 0 gradually from this argument. That means maybe what are the other parameters that can go? Obviously, charge and Planck's constant and mass are not going to change, right? So the only other thing left is carrier density or particle density. Maybe the particle density can change, gradually to 0. And what we'll see now is a superconductor. Another characteristic of a superconductor is even that cannot happen. That is forbidden as well. So neither can the phase change nor the particle density can change. Phase cannot change because of topological problems. Particle density will not change because it's a many particle effect, and we'll see right now. Physically, you can see if you have 10 to the power 20 particles in one state, it's very difficult to change the number because it's one state, right? If you want to change it by even a small amount, it will cost you a very large amount of energy. Just like, if you have a very heavy object rotating, it's very difficult to, if it's one object. If it's a lot of small particles that are rotating, you can, stop a few, right? But if it's a full one rigid object, it's very difficult to change it now, right? So that's physical meaning. Yeah?
I just wanted to make something clear. This is an approximation.
No. This is, we have...
it acts as one object.
This is not an approximation. That's correct. This is the only way we can explain superconductivity today. That it is one many-body exact wave function. It's not an approximation. In fact, in this argument we are doing now, there is no approximation at all. We don't have any magnetic field, so that's 0, and then we are left with only this. And now we see that, I have a problem changing the phase because it's, in a ring at least, it must come back to itself. So that can't change easily. And I have electron density, but now we want to see, I want to kind of give you a notion of why the electron density cannot change a little more mathematically, but we will look at this in a little more detail maybe in the class on Tuesday. Question?
Does it change anything if it takes 2 revolutions to come back to our place, like if it had a Riemann sheet?
That's a good question. So e to the power I theta, so you're saying if it takes multiple revolutions, yeah.
Is that even possible?
Say that again. What is, yeah.
Like, is it possible to have a Riemann sheet sort of scenario? I guess we don't.
Oh, definitely. If you have e to the power I theta, that's only in one plane, right? And you are asking whether it has some sort of Riemann sheet. Let me think about it. I don't think it does. It's it's a sort of single valued. It's not a spinor, where you need 2 revolutions to come back to where you. But here it's not like a spinor. It doesn't have 2 components, right? So right now it's just a complex number, and or in other words, it's a scalar. It's not a spinor at this point. Okay, yeah. Okay, so so now the last point I wanted to do before we kind of get a little bit into the microscopic picture is the following: that if I have why is it that the carrier density, or the Cooper pair density, if we want to discuss it that way, why is it that cannot change? So here's a slightly different problem, which shows how a particle number can change. And let's say I have a semiconductor and I have a conduction band state and a valence band state, or I have an atom and I have a ground state and a excited state, let's say, right? And these are the energies of the solid, and here's I'm going to plot as time. Okay, and so I put the electron at time t is equal to 0, single particle electron state in the excited state, right, p state, right? And then I write my wave function, combined wave function, as some constant of the p s orbital times psi of the s orbital plus some constant of p orbital times psi of p orbital. Does that make sense? I mean, just a linear combination of the two wave functions. And I want to track how is this thing changing with time. If I find that at a long times so what I'm actually plotting here is really not the energy. I should sketch it slightly differently. I'm plotting here the coefficient squared of a p of t whole squared, right? The probability of being it in p state or in the s state. Right? So I'm saying at time t is equal to 0, I have found that it is, like that. It's in the p state. And if I do that for a real hydrogen atom, what you'll see is because it is coupled to the electromagnetic spectrum, right, it can emit a photon, right? So it will transition, but it takes a certain amount of time, and that time you can calculate, so a p orbital wave function squared will go to 0, and this will grow and become 1 over time. And you can calculate exactly how much this time is using golden rule, and you'll get about a nanosecond. That's the order of magnitude of time it takes for a transition like this to occur, right? So in a normal atomic system, which is unable to explain why a superconductor carrier density and why such a transition is forbidden is not yet explained. Now, so in terms of the energy of the system, I think you can hopefully see in a certain way, if not exactly, is going to look like s orbital probability times the energy of the s orbital, right, plus p orbital probability times energy of the p orbital. That's the energy of the electronic system, right? And then you're leaking out energy into the electromagnetic mode, so maybe there is a probability that builds up into the photon that comes out. That part we're forgetting about that part at this point. But for the electronic system itself, this is how it's progressing. So the energy is going from energy as a function of time is going from a p orbital energy to an s orbital energy. And this is the most important thing here. It is a smoothly deformable transition. The a s squared and a p squared change smoothly with time, right? And it actually can take you from e of p orbital to the e of s orbital for the electron. It can be done smoothly. Okay, so I think I'm kind of a little running late on time, but it turns out that for the superconductor, this is not possible, impossible to do it smoothly. And the reason for that is the following. It's actually a very interesting reason itself, because these things also really all give you hints about what's going on microscopically. And once this is also why Landau and Ginzburg proposed what they proposed. They didn't come out of thin air. They really had a reason for that. So, and the reason it can go smoothly from here to there is because the energy in the single particle Schrodinger equation the energy depends on mod psi squared of any state. So if I have s orbital state, it goes as mod psi squared. Energy, if you go back to your Schrodinger equation, H psi is E psi, right? E psi and all that. And for the single particle picture, the energy, okay, I want to kind of say, is this clear? Energy should be proportional to mod psi squared, which is the probability density for any orbital. But in superconductivity, or in many particle, superconductivity situation, you get a very weird situation, and maybe in the next class I'll try to just show you why. It's going to become something like this. It's going to be k plus some maybe some other constant, and there'll be a fourth power of the wave function too. So that's very strange, but that's how it's going to be. There'll be a dependence on fourth power of the wave function, and that changes the game because if you have mod psi squared and you plot your landscape of energy, real of psi and imaginary of psi, and here's your energy spectrum, allowed energies, it's a paraboloid in this picture. Right? It has only one minima. Right? Does that make sense? It's a paraboloid in this window. If you have this, I mean, I've not explained why this is, but this will come because it's a many particle object. It's and all that, and it has pairs and that sort of thing. We'll come to that later. But here, if I go to the fourth power, and if I have a sign change here, something very interesting happens now. And I think maybe if you have talked about phase transitions in courses, you would have seen that if I have a sign change, this and this have different signs. You can have a situation where you form the bottom of a wine bottle picture. Right? So you get this sort of situation now, right? So the energy spectrum for such a situation with the real and imaginary part will look something like that. And maybe you can see right away why is it that in this case, if I release some particle here, it will obviously come down here very gracefully, right? But here, if I have a particle in the ground state, okay, so let me just explain this a little bit. So this is a you can revolve it around. So there's and what are we looking at here? We are looking physically, if the wave function of the state is here, then here's the angle. Here's the theta, and here's the amplitude of the wave function, right? And that thing it has a degenerate, meaning it can go around and not change its absolute magnitude. The carrier density will stay fixed. Does that make sense? As you go around the bottom here, the theta is changing, but where is my Landau-Ginzburg function? Okay. The theta is changing, but the carrier density is not necessarily changing. I mean, the magnitude is remaining the same around, right? And I think you can see to change the carrier density, you must pay a price, energy price, because you're sitting at the minimum of a well here. To change the carrier density, you must give it some extra energy now, right? And so there is a barrier to that sort of thing from happening. And in other words, if I were to sketch properly what the picture will look like here, you again have a situation where you have a superconducting current flowing, which is, say, persistent current, and here where you have no current at all. And if you look at the energy cost, it will be something like that. There's a barrier between the two. You cannot go from here to there without exciting it. You have to do something to stop it from carrying current, because it's in a stable state. It's in a stable state, and yeah.
Do you need to excite the entire state here to get over that, or just the individual group of pairs?
Yeah, so that's a very good question. So the picture of superconductivity is that what we have learned till now with BCS theory is you don't have access to an individual Cooper pair. You have access to all of them in one big blob. If it's one object, there are many Cooper pairs, but they are all entangled in certain way, and it's like instead of individual sticks, you have a big ball of sticks that are mechanically tied together, and they all move in one go. I mean, you can't change them individually.
So
Yeah.
entire energy that you would need to overcome, you can't have it just randomly pop out.
Right. So as a result, this energy barrier can be very high because it's the sum of all. Energy of each one of them, you just sum all of them, so it grows, and it's a large energy barrier as a result. If it was a single particle, you can imagine that maybe I have a 1 MeV, for one particle, I can easily surmount it. But now that 1 MeV gets multiplied by the total number of particles. So that's why the barrier becomes very large to change. That's why it's resistant to change. So, yeah. Okay, so one last point. I haven't even started talking about the microscopic picture. That we'll do on Tuesday, right? On Tuesday, where we'll basically give the basic idea of the BCS theory, and we'll see that we can explain the superconducting gap and those things very simply by looking at one of a particle in a box problem, pretty much, and we'll use kind of a delta function, and we'll show how it gives you all the necessary explanation. But one last thing is that if I let me just make sure I not right. So forgetting what I wanted to say. So okay, so there's a cost to that as well. What are the methods by which you can actually break superconductivity? Clearly, temperature is one way. Right? And actually, when I say the magnetic field is expelled, if you increase the magnetic field beyond a certain okay, so forget about that for a second. There is another factor by which you can kill superconductivity, and that's by if you continue to increase the current that flows. If you continue to increase the current that flows, if you try to push more and more current through it, there's also a critical current above which it becomes a normal metal. And that is also tied to the fact that there's only a certain magnitude of a magnetic field that a superconductor can expel. If you exceed that critical field, the superconductor will again become a normal metal. So there are three critical things. There's a critical temperature, there's a critical magnetic field, and there's also a critical current density that can flow through a superconductor, and they're all tied to each other. They're related to each other, of course. Right? So yeah. Okay. So one more thing I just wanted to add is this discovery was made by maybe in the last 5 minutes I'll just give you a summary of what I want to do on Tuesday. Okay, but hopefully at least qualitatively we are clear of where things are. And what is the major change? The major change is we introduced a wave function and just said that this works for every electron, and there's only one wave function. And that is really the qualitative change, and that explains many of these features already. You can see, I mean, the Meissner, the resistant to change, persistent current. Yeah.
So how can we account for aspects of correlation when we would just have one wave function describing the system?
Right. So this is always very difficult to kind of also digest, right? Because you see, we have no problem thinking Y is an electron in a hydrogen atom, S state, P state. I have no problem with that, right? But you know that, or protons and all that, but we also know that electrons are not necessarily, electrons are somewhat elementary particles, but protons are not, right? They're also composed of many quarks. Electrons are composed of quarks. So there are already many particle objects. So in that sense, this is a another level of. So if I have 10 to the power 20 of maybe 10 to the power 20 quarks, and if I'm calling that one particle, right? I shouldn't have a problem calling 10 to the power 20 Cooper pairs as one particle either, right? Because from a conceptual perspective, it is a many-body state. And it is just like an atom or just like an electron, which is stable in a hydrogen atom. In that sense, this is quality. Now, correlation, of course, what we'll find is not all the electrons in the metal participate in this business. It's only a very small number of electrons, rather a small fraction of those electrons. And what we'll see is if your metal Fermi level, let's say, is like 15 eV or 10 eV, okay? What we will see in the next class is the amount of electrons that actually form Cooper pairs is within a window here, which is related to the phonon energy, or a Debye, let's call it a phonon energy. Let's say an optical phonon energy. That's the window of, instead of kT, there'll be a h bar omega here. And what we will find is there will be a gap formed in a. So essentially, what does that mean? It means all the other electrons here internally are acting as normal electrons. They don't even know they're inside a superconductor. They're deep inside the Fermi surface. And Fermi surface, so all the superconductivity is a transport phenomena, so it only happens on the surface of the Fermi, sea here, right? Only on the surface. And what we'll find is this gap we have talked about will be related to the this phonon energy, right? But if it was the phonon energy, we would be golden now, because we would have room temperature superconductors, because we have materials with phonon energy larger than kT. But unfortunately, there's a factor here, which will look like this, n times the density of states. And this factor is what makes superconductive transition temperature 2 Kelvin instead of 200 Kelvin or 2000 Kelvin. So we'll see that, and that's what will come out of the analysis, microscopic analysis. This was really the major result from Cooper and the BCS theory. But the way he really realized this is, if I here's kind of the hint to how they solve the problem, and that comes from this relation here, right here. This is a perturbation theory result, and they said that well, physically you don't have to look at the formula. You have a lot of states deep inside the Fermi level, a lot of electronic states allowed, right? And if you look at the K space, you have a Fermi circle, a Fermi sphere, right? In 3D metal, Fermi sphere. And what we will see is, internally, deep inside, there's not much action, but when electrons are, opposite ends of the Fermi sphere, they can interact with each other. The interaction for two electrons with opposite spins on the diametrically opposite ends of the Fermi sphere will be the strongest. And there's a reason why they interact, because their interaction strength will be the strongest. And they will interact by emitting and absorbing optical phonons, phonon exchange between the two. And when that happens, so that's, you can think of it as a perturbation, if you might, and this is a term, this is your perturbing term now. And the picture there is very similar to what we had discussed a little bit in the last class, that you have an electron that emits a phonon, and another electron picks up that phonon, right, and transmits. So this combined object of two electrons effectively and the phonon in between is the Cooper pair. And if I look at this, the energies of the Cooper pairs, what you will find is, if I have a lot of energies very close to each other, which is a representative of all the K states that are going all the way from the center, and I add a weak perturbation, very weak perturbation, what happens is very strange, and this was observed by Cooper for the first time in 1954, and he has a short paper on it, like a very short paper. If I have a very large number of states here, by the way, I've also posted his this article, so please read it, because this is something it should be relatively simple for you to understand, right? And in this lectures here, you can read the part for Cooper, because what he explains is very interesting. He says that if I introduce a very small perturbation, and I have a very large number of states here, let's say big N, which is 10 to the power 22 or something like that, and I add a very weak perturbation, what happens is one of these states in the bottom is going to split from all these states above. Only one will split, and it will come down by n times the perturbation. It gets really pushed out very low. When I say very low, it's not very large in energy, but it really gets pushed down by the combined strength, if you might, of all the other states. Combined strength, it just gets pushed out, right? And a question? Yeah.
Does that just come from this interaction?
Absolutely, it just comes from there, really. Yeah. Exactly, it just comes from there, and that's why I wrote it there, and it gets pushed down, and this is going to be a gap, superconducting gap. This, and this state would be really all the Cooper pairs, and then there'll be an excitation gap to go there, and because of this state is well protected from all the others, because this energy difference is very large, and or in other words, this thing here, this energy difference between the superconducting state and all the excited states is very large. The denominator is large, so this thing is small, so the state is very rigid. It's not changing because this term is extremely small. That's the physical way of looking at why, and that's what was realized by Cooper. And immediately after that, they and Schreiber had a very nice also realization I think he writes, if you read it, he writes that he was in a subway in New York City when he got this idea, that how he could introduce, this Cooper pair idea using these annihilation creation operators and all that. But essentially, it's a synthesis of what Cooper discovered first about, why should it actually split like that? Why should there be a gap in the first place? The fact that there is a gap, though, was older. I think you can see electronic susceptibility and Landau-Ginzburg and all, but they never, all the earlier theories never told you what is the microscopic picture of this, right? And that was given by Barton, Cooper, and Scheff. So that's something we'll do in the next class, and then we'll look into, we have all the arsenal we need to explain it now, so it shouldn't be a problem, okay? Okay, good, so let's meet on Tuesday, and by the way, next Friday, you are doing the hard work, your project first presentations, all right? And I sent you a little link for writing up your first report as well. First report can be 1 page short. Just I want to get you started on it. So. Okay.
So what time?
Thank you. Oh, thank you. Yeah.
Will they be at the same time?
Yeah. So next week around 5, but maybe I'll make it 5:30. Looking at the time, we may not. I'll send out an email, but it will be in this classroom, and that will probably be the last time we're meeting here in this room, meaning on Fridays. Yeah. Okay, good.